Well, we look for the biggest change, you know, compared to the smallest initial. We look for the biggest x and the smallest initial. And so when I look at that, the biggest x is going to be 2x, and the smallest initial is 0.100. And so if I define it as the change is small, that is 2x is much smaller than 0.100, then all these are going to have a smaller change and a bigger initial, meaning that if I define it like this, all the other ones are the same. So this is what I mean by doing this. So that means that 2x compared to 0.200 is small. And therefore 0.200 minus 2x is going to be about 0.200. So this would be like a swimming pool, lose 2 drops, we're going to be left with about 0.200 squared. And then 0.200 minus x, well, it's like a swimming pool minus a drop of water, it's going to be about 0.200. And then 0.100 plus 2x should be about 0.100 squared. And then 0.300 plus x is about 0.300. All right, so our simplifying assumption got rid of the binomials, and then try to solve them. 2.67? 2.67 is equal to 1.48. Does that sound right? No, and then there's another problem. Is 2.67 x? No, 2.67 is just that. Yeah, and so there's the problem here is that simplifying assumption fails in this case. It fails because there's no x to solve for. So we can't use the simplifying assumption, right? X is going to drop out of the equation and we can't solve for x. You see that? So what should we do here? What should we do here? Yeah, successive approximations? Or is there something else we might be able to do? Something else. I guess we can't really cancel any of these out, and we'll make it easier. Well, there is something else that we can do that doesn't take that much time, that might make successive approximations a little bit easier if we have to do that. We can't divide. Yeah. In this case, no side is biased, right? No side is biased, but we could try to reset. This resetting has a different purpose. This reset is to eliminate binomials. One. And two, this reset is, you know, what's your first guess going? Well, your first guess is going to be quite small, right? Well, how small? You know, when we're looking at small changes like that, pretty soon we're going, oh, are you going to start off at 0.001 or 0.001 or 0.0001? You know, where should you start? Another reason to reset to eliminate the binomials is so that we could get a decent first guess. You know, it's not going to be a great first guess, but we can get a decent first guess by using the simplifying assumption, which will fail. You know it's going to fail because if we reset this, well, what side should we reset it to? Well, this looks like it's biased towards the product side a little bit, so let's go ahead and reset it to the products. And so let's come up with a new initial conditions. This will be the reset. So we have 0.100. What's our limiting reagent? The copper or the tin? The copper. So we lose all our limiting reagent. And so this is going to be 0.100 we're going to be left with 0 here. How much tin will we have? .25? Yeah. All right, so if we know 2x is 0.100, then x is 0.050. And so this, actually, we're resetting it to the right, so we're going to lose 0.050. That's right. So this is minus 2y. Right? We're just going to eliminate these two lines here. Minus 2y minus y, where y is 0.050, plus 2y. So this is going to be 0.300. And plus y. So this is going to be 0.250. The other reason is, if we just go ahead and reset it, do we have to calculate Q now? It's not necessary to calculate Q because if you have a 0, you can't go lower than 0. You're going to only go up. So this side we have to add 2 because we have to increase from 0, right? And so I don't have to calculate Q. I know it's going to be plus 2x molar plus x minus 2x minus x. And so at equilibrium, I'm going to have 2x molar 0.250 plus x 0.300 minus 2x 0.250 minus x. As long as I make sure everything, is balanced, that is, I'm not losing or gaining atoms, and this is fine. I could start the equilibrium anywhere I want. You should get the exact same answer. All right, so this is going to change the Kc expression. It's going to be 0.300 minus 2x squared 0.250 minus x over 2x squared 0.250 plus x. All right, we can't have all binomials for, if the simplifying assumption works, we have to have x in a term like this. All right, so now we're going to assume the simplifying assumption, right? We're going to assume what is much smaller than what. And so which one of these is the biggest percent change in the binomial? 2x from 300 or x from 250? 2x from 300. So we're just going to assume that 2x is much smaller than 0.300. And then this should simplify into this. 0.300 minus 2x is 0.300. It's going to be squared 0.250 over 2x quantity squared 0.250. All right, now the math looks a lot easier, right? It would be nice if it worked, but we'll see if it works or it doesn't. So,
why are you limiting the 2x squared
if I get rid of the 2x, then you're saying that, yeah, you're saying that 2x is small compared to 0. Or you're just arbitrarily defining 2x as 1. All right, solve for x. Give me one more digit.
4.
4. Actually, one more. We're allowed.
0. 1.
1. 4, 1. 1, 0, 3, 4, 1. All right. right, so now we're going to calculate, we need to justify this. So we need to calculate the percent change. Percent change is equal to the change over the initial times 100. And so the change is 2x. And so let's double it. It's going to be 0.06082 over the initial, which is 0.300 times 100%. And so what does it amount to? Percent change.
Twenty point 3%.
20.3%? Okay, this is greater than our cutoff, our arbitrary cutoff of 5%. And so it fails, the essay fails. Although the essay failed, we didn't waste too much time, right? We didn't waste too much time. And this gives us a good starting guess for successive approximations. And so the good starting guess, if essay fails here, then we have to use successive approximations. Using successive approximation, I'm going to guess that x is equal to 0.03. And then figure out what the k value is, etc. All right. We knew it was likely to fail because it should be more even. So pushing all the water to one side is going to change that. You got a different answer?
I got 0.1233.
Well, 0.1233.
You get that if you do 2 instead of 4 at the bottom. And
Okay, 0.1233?
Yeah.
All right. That looks better. 0.1233, which is going to make this even worse. Maybe this isn't going to be such a good first guess. We're going to double this. 0.2466, which is going to give us what percentage?
41.
What is it?
41.
41%. 41% is pretty bad, so our first guess here, we do our first guess at 0.1 and then go on from here. I'll let you finish this. Normally I just, will reset it and then try the simplifying assumption. And so that's what I normally do. Oftentimes that works fine, saves you a lot of time. Sometimes it doesn't work, but the amount of time you waste isn't so big. 82%?
246 is really close to 0.3.
Oh yeah, it should be. It should be higher.
Double that. There you go.
82%. Still, that guess is going to be way off. All right, so the simplifying assumption failed. We reset it, but we reset it for a different reason. All right, so for Chem 1B stoichiometry, you use this. You know, the K is, this is Kc. K is the concentration of G, little g, H, right, etc. This is what we call a law, right? Does the law come from theory? Where do laws come from? Experiment, observations. Laws come from observations. So this is the pattern that people will see. The pattern for gases is the same. You know, Kp. Just instead of using molar, we use atmospheres or bars here. You know, but the setup is the same for the ice table, etc. And so we need this because this is going to tell us where the reaction is going to end. And so what we want to do is we want to figure out, you know, we need the K's, the numerical value, right? The number value. And so where do we get the K's? You know, how are K's determined? Well, number one, they're determined by experiment. You know, you run a series of experiments, experiment 1, experiment 2, experiment 3, whatever, and then average the values, like 1.48, 1.48, 1.47. Do you want to do an experiment for every single reaction, or do you have to? Do you have to do an experiment? If you want the K value of an unknown, that is an unknown K value for a particular reaction, how can you get it? Do you have to do experiments in order to get it? No. There are other ways. For example, if you wanted delta H, do you have to do a calorimetry experiment, or are there other ways of determining delta H for a reaction? There are other ways of determining it, you know. And so, look at other methods. You know, we can calculate it.
Oh yeah. Dr. Deval, this is known as Hess's law. So we get K from the reaction we know, and we add those up to get the reaction that we don't know, the K value.
Yeah, well that's for Hess's law. It works for delta H and energies. You know,
No,
so
it's done in a similar way to Hess's law.
yeah, except it's a little bit different than the Hess's law. It's a little bit different because let's say we multiply it by some coefficient. In Hess's law, if you double, let's say you burn a mole of methane, it gives you this much energy. If you burn 2 moles, you double it, you're going to get twice as much energy, right? What about the K? If you double the equation, what's going to happen to the K?
Raise to power 2.
Yeah, it would be raised to the power rather than. And so here, if you cut it in half, then we just take the square root of K, of the original K. And so that's what we end up with.
Yeah, I mean, it's a similar way to Hess's law.
It's similar, but it's different.
Yeah.
And so the reason I'm emphasizing the difference is because people still end up doing this. They write NK instead. It's not NK, it's K to the N. Right? In Hess's law, it would be NK. And so this is the difference. It's not exactly the same as Hess's law, but it's very similar. It's analogous to Hess's law. In Hess's law, this would be negative K. It's not negative K. For us, it's
1 over.
1 over K. Right? And then if we were to add equation 1, so let's say equation 1 had K1, and then equation 2 had K2. If we add this, then the K for the sum, which we'll call equation 3, the K for the sum is equal to what? K1 plus K2? In Hess's law, it would be K1 plus K2. You add them, right? If you add the equations, you add the delta H's. But for us, it's not. For us, when you sum the equations, what do you do with the K's? You multiply them. So this would be K1 times K2. And so it's similar, but it's different, you know. And so it's like Hess's law. And so what this means is you don't have to do experiments for every single reaction that you want a K value for. We can do that based on this. There's even more. But we'll have to wait until chapter 20. It's thermodynamics. To look at, there's even easier ways. Getting. All right, so those are your basic equilibrium calculations, so stoichiometry. 1B. Are we good? So I want to move from chapter 15 to chapter 16 today. It deals with acid. But we aren't just going to focus on acids. We're looking at how to solve these equilibrium problems. And so in chapter 16, we're going to be introduced to multiple equilibria occurring simultaneously. You know, what happens. And so in chapter 16, acids and bases, let's take a look at this. I want 1.0 times 10 to the minus 8 molar HCl as an introductory example to this. Do you know how to calculate pH? pH is the negative log of the hydrogen or hydronium ion concentration. In chapter, 16, we're primarily going to be talking about, rather than hydrogen ion, hydrogen ions are unstable in water. Because hydrogen ions is just a bare proton. Bare proton is extremely reactive. It'll automatically react with water, form hydronium. And so in the Chem 1A review, I like to use H+, because it's easier. But in chapter 16, we're primarily looking at hydronium, the way we write the equations. So looking at hydronium. And so somebody calculate the pH for me. You know what P stands for? The power. And H stands for H+ concentration. The power. Actually, it's not the power, it's the negative power, really. The negative of the power. pH is 8, right? So if you look at the power, the H+, the power is negative 8, but we take the negative of that and it gives us 8. Do you know how many sig figs we have in power functions? Like this. When you look at this, how many sig figs are there? It looks like there are 2 sig figs, 1.0, right? How many sig figs are there here? Right now I have 0 sig figs. In power functions like this, the sig figs are after the decimal. And so if I want 2 sig figs, I'd have to write 8.00. This gives me 2 sig figs, because this is just the power here, the 8. And the coefficient part comes from what comes after the decimal. So this is 2 sig figs here. All right, let's talk about the pH scale. The pH scale ranges from what to what? pH scale ranges from 0 to 14, and in the middle is 7. Yeah, 7 is neutral. And above 7, we call that acidic or basic?
Basic.
Yeah, so this is basic. And then we have, strongly basic here. Now let me ask you this. Can the pH go above 14? Yeah, the pH can go above 14 because, pH of 14 is just 1 molar sodium hydroxide. Can you make a more concentrated solution than 1 molar sodium hydroxide?
Yep, 19 molar.
Yeah, okay.
Extremely concentrated.
Where did you come up with that number, Kelly?
I just feel like looking up molarities.
19 moles of sodium hydroxide. Each mole of sodium hydroxide is a 23 plus 16 would be 39 plus 40 grams a mole. And so 19 moles would be 19 times 40, or 20 times 40, 800 grams. 760 grams. 760 grams per liter. Wow. It's a lot. Yeah. I don't know if it's that soluble. You might not.
Be careful with it.
Right. You might not be able to make 19 molar. It might be too concentrated.
Oh yeah, how about 18 molar sulfuric acid?
Before
Yeah.
you erase that, did I miss something on the pH at the bottom there where you put the two significant figures as the zeros? Isn't it 1.0 is two sig figs and then the pH? I missed what you said about why you got two zeros.
In power functions, the sig figs come after the decimal.
Got it.
Everything before the decimal in a power function is insignificant.
Got it. So the two represents the two. Okay.
Yeah.
Okay.
So we have matching. We have 2 sig figs, 2 sig figs.
Mhm.
We could have pHs higher than 14. But what happens? The reason, why don't you hear much about pHs higher than 14? Because like 6 molar sodium hydroxide is very common. We call 6 molar dilute, But 6 molar sodium hydroxide would have a pH greater than 14. And then we could have pHs. Can we have pHs lower? Can we have negative pHs? And negative pH is possible. Like here, we start getting to negative pHs less than 0.
That's really acidic.
It's really acidic. I mean, a pH of 0 would be like 1 molar HCl. 1 molar, can we have 6 molar? Yeah, 6 molar is considered dilute HCl.
12 molar.
6 molar has a negative pH. Is that possible to have negative pHs?
I guess.
This is always very interesting.
I know.
Like in Chem 4, you would have never heard of pHs, negative pHs, or pHs greater than 14. Why?
Give us an idea of the scale.
So what if it goes lower than 0 and higher than 14? You just say. The reason I ask this is because a lot of Chem 4 students, they tell me that pH less than 0 is not possible and pH greater than 14 is not possible, and I wonder why.
Not with this scale.
Hmm?
Not with this scale. You can't see negative logs. Right?
I mean, you can. I mean, we don't take a negative log, but this is it. If we have let's say a pH, let's say the pH is negative 0.4. So if we have a pH of negative 0.4, what is the hydronium concentration? It would be the anti-log. It would be the anti-log of the negative pH. So this would be the 10 to the... So that's... would it be negative 0.4 or positive 0.4? Positive. This would be a negative times a negative, right? Is a negative pH. And so we could have it. And so it is. You should Google what the most acidic natural body of water is, and see what the pH is. I think, I forgot where it is. I thought it was close by, not so far. The one from one of these volcanic vents.
Got it. The sink of Jiffy Lube. I like that Jiffy Lube.
Okay. I'll tell you why. Because if we stay between 0 and 14, you know, if we stay between 0 and 14, then we can assume all the solutions behave ideally. If we go outside the 0 to 14 range, then the solutions start to deviate from ideal behavior. How do solutions deviate from ideal behavior?
They're not all, it's not all in solution, it's not all valued. That means there's some concentration, there's some parts of the solution with pure HCl or pure sodium oxide. If the solution is greater than
Okay. Yeah. You're going to find other species, that's for sure.
Is that kind of like how on the bonus question of the exam, the carbon dioxide and the water and the carbonic acid, how it's in equilibrium? Is that somewhat similar to what's happening with if you have a high pH?
Not really. Not in this case. That would be something different because this concentration is still very low. I'm looking for different, that's part of it, but I'm looking for a different way of phrasing it. You know, when solutions deviate from ideal behavior, typically what's happening? I'm talking about end of chapter. I got my book here. I'm talking about the end of chapter 13. The very end of chapter 13, at the very end of Chem 1A. At the end of chapter 13. Most people don't spend that much time talking about it. But at the end of chapter 13, what was covered? Well, not the colloid stuff, because that's at the very end of chapter 13. It was the stuff before the colloids. It wasn't about the supersaturated. It was about the something else. Let me give you. Do you remember something called the Van Hoff factor?
Yeah.
Okay. Do you remember how the Van Hoff factor changed with concentration?
Yes.
You do? So.
I just heard of it.
Okay. So, do you remember what it was about? What all that stuff was about? How solutions deviate. This is like, how do gases deviate from ideal behavior? And solutions are very similar in a certain sense. One of the big things that causes gases to deviate from ideal behavior are
High pressure.
intermolecular forces of attraction. You know, ideal gas, you expect no attractions between the gas particles. Ideal solutions, you predict pretty much the same thing. There are no attractions between the solute particles. But what happens in non-ideal solutions are that the particles tend to pair up. Some solutions deviate dramatically from ideal behavior. For example, you know, even something like acetic acid starts to deviate quite a bit, like benzoic acid, those, because what happens is, you know, the strong hydrogen bonding interactions between the molecules, and they tend to get stuck together. They do something called dimerize. Have you heard of dimers before? Dimers are like when you take two and make it into one. That's a dimerization. There's something like polymerization was you take, you know, a whole bunch of monomers and then make it. Well, it tends to form these, so these strong hydrogen bonding interactions hold these particles together. So you might have like what you think is 0.1 or 1 molar acetic acid, but the molecules are all kind of stuck together. And so we have something called the activity. Have you heard of activity? Before. I want you to read this for me. I want you to read 13:9 It's only 2 pages. Activity.
It's in Reading.
Hmm?
It's in Reading, the most huge.
It's in Reading? Yeah, I thought it was nearby.
Reading, Northern California.
Right, there's some kind of
It's
volcanic.
got a pH of minus 3.6.
Yeah, that's a horrendously low pH. It's minus 3.6. You wouldn't want to go swimming in that. Probably.
Just west of Shasta County.
Okay, thanks for looking that up. Yeah, I looked it up a long time ago. I just couldn't remember it. All right, so what tends to happen is as we get to the extremes, we start to deviate from ideal behavior. When you start to deviate, no big deal, but you know, if you're using equations that presume that things are behaving ideally, is it okay? Like, for example, if you know that your gas is deviating, you know, significantly from ideal behavior, are you going to use the ideal gas law to do calculations? No. So if you're at a pressure of 100 atmospheres, I wouldn't even bother with the ideal gas law. I'd probably use the, what equation? Van der Waals, right. I'd probably use the Van der Waals, the much more accurate answer. Well, what are you guys going to do if your aqueous solution starts to deviate dramatically from ideal behavior? You know?
Like 19 molar sodium hydroxide.
Right, 19 molar would be way out there. I mean, I'd expect my calculations to be way off. If I'm doing 19 molar sodium hydroxide, I think my calculations are going to have a significant error associated with them. Because when we start to deviate from ideal behavior, we cannot use our ideal molar concentrations. You know what we have to use instead of our ideal molar concentrations? We have to use activities. All right, we can't use our ideal, we got to use our activities. Well, how do we get our activities? Getting activities is beyond the scope of Chem 1B. And so if we're starting to be at these extremes, then we just say, hey, our calculation is going to be way off, most likely. Okay. And if we want to do a more accurate calculation, then I better do some learning about activities and how to factor those in. So what we're going to do is we're just going to assume it behaves ideally. And sometimes, yeah, it should behave ideally, and our calculations will be great, you know. All right, so if we go less than 7, it becomes acidic, and then strongly acidic. And so how would you classify 1.0 times 10 to the minus 8 molar HCl? Slightly basic.
So we just got pH.
Yeah, and so pH of 8.00 is slightly basic. Uh-huh.
What would you classify, like what does pH still work for superacids and superbases in a different form?
Well, superacids and superbases in water are the same as strong acids and strong bases. They're no different. The only way that superacids and superbases are different are in non-aqueous solvent. You get non-aqueous solvent, then they can behave as a superacid. But all strong acids, including superacids in water, are too unstable to exist in water, and they're going to hydrolyze water to form hydronium. And so there are a whole bunch of non-aqueous solvents that people use for those. For example, for my superbase, which I used to work with a superbase, I was using liquid ammonia as my solvent. I just get a little flask of the liquid ammonia. It was a very cold temperature, everything was cryogenic. Uh-huh.
How do you get a pH of 8?
How do I get a pH of 8?
Yeah, you didn't do the log or anything.
No, we did. I did. Well, somebody did it for me. Somebody just. Why don't you just do it? Punch it in your calculator.
When you log that number, it comes out to be -8, but it's negative.
Yeah, then you need to just change the sign. Of course, they would never give you this problem in Chem 1A because, does it work? Does this work? Is it because the, you know, there's something not right here. What's not right?
It's an acid at basic.
Yeah, if I put acid in water, shouldn't the water become acidic rather than basic? Yeah, the water is supposed to come out acidic, not basic. So, would you attribute this? I love this answer because everybody puts this at the end of the report. Experimental error. This is due to some kind of experimental error. You know, maybe the pH meter wasn't working right, or maybe I mixed something wrong, or, you know, experimental error usually covers all your bases. Yeah? No, I'm sure you get tired of somebody trying to explain this as experimental error. This is not experimental error. What is it?
Due to the
Oh.
polarity of water or something.
What? Polarity of water?
Or equilibrium on it. Switches the H plus
Yeah, I guess polarity will have something to do with its reactivity. The reactivity of water is going to impact this. But did you have another one?
Makes it hydroxide ions, right? The water. So it's the same fluctuation.
Water makes hydroxide ions, but it also makes hydronium ions. And so a pH of 7 means this. A pH of 7 means that the hydronium ion concentration is equal to the hydroxide ion concentration. That's what a pH. And so basic means that we have more hydroxide than hydronium. And acidic means we have more hydronium than hydroxide. Let's look at pH scale tells you. All of them will have hydronium and all of them have hydroxide. And so if we add some hydronium to this, shouldn't it come out more? Because if water is hydronium and hydroxide are equal, and I add hydronium by adding HCl, shouldn't it come out more hydronium than hydroxide? And so if you were to explain this, would you have an explanation for this? Because something's not right. How can you add acid, a strong acid? Chloride's so weak of a base, it's neutral. How can you add a strong acid to water and get the pH to go up?
Is it maybe because it's such a low concentration? I think the net -8.
It is a low concentration, right? But still, it's hydronium. It's still going to increase. Even if it increases just slightly the amount of hydronium, you know, because this is 10 to the minus 7.
Does it also increase the sodium ions?
This is 1.0 times 10 to the minus 7 molar at 25 degrees C.
How about impurities in the water?
Yeah, I guess we can always explain it due to impurities, but what impurities? They have to be in higher concentration than the HCl.
That's true too.
I guess if one of the impurities is sodium hydroxide, and I have more sodium hydroxide than HCl, but that's a chemical reaction there, we should be able to figure that out.
Uh-oh.
Well, if it's aqueous hydrochloric acid, aren't you adding more water to the solution too, since it's such a low concentration?
Wouldn't that make
No,
it
I can just
neutral
add
on
gas.
basis?
I'll add gas and have the volume stay the same, roughly. But do you have an answer for this? Why am I adding strong acid and getting a basic pH? If I keep adding the HCl, is the pH going to continue going up, or will it curve around and go down? And where will it curve around and go down?
At minus 6.9.
So obviously they're going to avoid this. They aren't ever going to give you this problem in Chem 4, right? Because it'll mess you up. And then you think you won't know anything anymore because you thought you had it all figured out, and then they throw something like this and mess you up.
So because the half reaction is more favorable than
Well, the half reactions have to be balanced. So if one makes hydroxide, the other's got to make hydronium.
The minus 8 power had to be to like minus 6.9 to make it acidic.
Yes.
So it has to be larger concentration.
Okay, so then the pH goes up and then it goes down. Is that how it works? No, that's not how it works. Basically, it's this. This kind of calculation is too complicated for a Chem 4 student. And so best not to say anything about it and just avoid it entirely, right? Because it is too complicated. And if you were to tell a Chem 4 student how to do this, it'd be too much, maybe. But the problem is, this is the problem that we're having. We have multiple equilibria happening here. When we have multiple equilibria, there are different things we do. Like, if the multiple equilibria are independent from one another, if the multiple equilibria do not depend on each other in any way, then we treat them separately, like separate problems. And so it would just be like solving one problem, and then solving another problem, and then solving another problem. So an example of something like this might be, let's say if we have CO2 and water, let's show liquid. You know, the K for this is going to be quite small. We're going to get some carbonic acid. K is small. The small just means it favors the reactants. We have this CO2 gas. And then at the same time, we have NO plus O2. Let's go with 2 NOs, and then this yields NO3. These are gases, all gases here. Do these equilibria depend on one another? Impact each other in any way? No, and so we treat these as separate problems. So we'll do the ice for problem 1, whichever one you want to do first, and then we'll do the ice for the second one. They don't impact each other at all. The other scenario is when we have multiple equilibria with something in common.
I'm sorry, at the end of that one, would you just add up all the K values to figure out?
We wouldn't add these equations. Don't add the equations. Don't multiply the K values. You just treat it as problem, 1. This would be problem 2. But 2 separate problems. Don't add, don't do anything. And so we have an ice table for this, and then an ice table for this. All right, and so if we have multiple equilibria with something in common, then we have to solve the equilibria simultaneously.
That's hard.
Let me put a little asterisk here. Solve. You're right, it's hard. We have to solve it simultaneously. That's a proper way to do it, but there are some tricks that we can do to save us from having to do that. And so what are the multiple equilibria? Well, these are the multiple equilibria. One is the water equilibrium. You know, water collides with water. This is what causes the pH, right? This forms the hydronium and hydroxide. Water plus water. This equilibria has a K value. Everybody should memorize the K value for this. Does anybody know? Well, each one of these, this is 1.0 times 10 to the negative 7, 1.0 times 10 to the negative 7. So what we call the ion product with the concentrations, the product is 1. Now, we have something interesting here because this Kw value is this. It's going to be the hydronium ion concentration over the hydroxide ion concentration divided by what? The water concentration? Divided by the water concentration? Do you know what the water concentration, you know what the concentration of water is in pure water? So if I had a liter of water, how many moles do I have? Pure H2O liquid. If I have the liter, how many grams of water is in a liter? Okay, so I have 1,000 grams per liter. And then we know a mole of water weighs 18.02 grams. And so this gives us about 55.5 molar. And so I could get about 55.5 moles of pure water in a liter. Does that molarity change much if I add a little bit of salt to it or take a little bit of salt out of it? You know, if I have, let's say, 0.100 molar sodium chloride, it's pretty much close to pure water, right? Well, not pure, but close. And so this stays at 55.5, so it's about 55.5. The change is very little. If I add a little bit more salt, take a little salt out, it's still around 55.5 molar.
Wait,
Uh-huh.
there's 1,000 grams in a liter?
Yeah, of water. Uh-huh.
So why do you have hydronium and hydroxide over water? And
It's a products of reactants.
oh, I see.
So what we do is this. We say this. You remember the van der Waals equation for gases? Yeah, I know, so long ago. But do you remember what it was for?
It was specific. It was to determine the radius.
Maybe you just remember. It was kind of complicated, right? Kind of complicated. And so we had an equation for ideal gases, and we had an equation for real gases. You remember that? Okay, now I'm going to make a leap ahead. Did you derive the van der Waals equation? No. Well, you know what? The van der Waals equation is an empirical equation too. It just came from observations. You know, ooh, the ideal gas law deviates this much. We can factor that in, right? Okay. So we have the equation, what we'll call the equilibrium law for ideal. The equilibrium law for ideal is just the concentrations, right? And then we'll have the equilibrium law for real solutions and real gases. You know, the same goes for gases because gases can deviate. And so the equilibrium law for real looks like this. It's A sub big A raised to A sub big B raised to the little b, dot, dot, dot. Oh, sorry. I got this upside down. G to the G, H to the H, dot, 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 over A to the little a, B to the little b, dot, dot, dot. Have you ever seen these little A's before? the little a's come from chapter 13, section 13.9. This is where A is the activity, not the molar concentrations. We've got to use activities. You know? And so you should know this. The activity of a solution is about equal to its molar concentration. Unless the concentration gets very high. If the concentration is very high, take a look at the Van Hoff table. When you look at the Van Hoff table and you see as the concentration gets high, it starts to deviate from, actually I should show you the Van Hoff table, rather than talking about it. When I talk about the Van Hoff table, I can picture it in my mind, but it's because I've seen it so many times. But probably when you hear Van Hoff table, you probably don't know what I'm talking about. But let me tell you what I'm talking about here. When sodium chloride is dissolved in water, how many ions are formed? 2. Right, and so if I had 0.1 molal sodium chloride, I expect 0.2 molal ions. This is what we call infinite dilution. This is ideal. Infinite dilution, everything should behave ideally. And so this is ideal. But when we get to something like concentration of 1.0 molal, it becomes actually 0.2. Well, take a look. We're out of time, but I want to say something before I need the molar concentration. The activity of gas is approximately equal to the partial pressure of the gas. The activity of a pure solid is equal to 1, and the activity of a pure liquid is equal to 1. Activity is called the effective concentration. Effective concentration. And so this would be the equivalent of the van der Waals equation for the equilibrium law. Right? If we knew we're deviating from ideal behavior, then we should use this equation, not the equations that we had on there. Now, looking at this, we have these two are pure liquids. And so whenever we have solids or pure liquids, their activities are 1. So this just ends up being hydronium times hydroxide. Here.
Having an activity of 1 is ideal? Or is it not?
Activity of 1 just means that it doesn't change much. You know, okay, let's say I had a gallon of milk, right? It's pure milk, 100% milk. I drank half a gallon of it, and so I'm left with half a gallon. Did the concentration get cut in half? No, it's still pure 100% milk. That's what activity means. Activity means it is effective concentration didn't change. All right, Raheem, announcement?
Okay, hi guys. So it looks like we're on chapter 16.
We're on chapter 16.
Okay.
I'm doing the 1 times 10 to the minus 8 molar HCl.
Oh,
The pH 8.
I see. Okay.
Which
great.
I'm sure I did in your. I always do the same one
Okay.
first.
All right then.
Okay. Yeah, go ahead.
All right. So I just wanted to make an announcement that I posted the chapter 16 worksheet online. It's a really big document. It's actually 15 pages this time. So I don't really recommend that you guys print that out because it's like too many copies, too many pages or whatever. I made some announcements on Piazza that this Tuesday's workshop, we're going to cover ice tables in depth, understand how to do them. We're also going to finish off that problem we were doing with successive approximation. So you get those skills up on solving problems with successive approximations and really large polynomials and whatnot. In the last 30 minutes, we're going to cover a little bit of this stuff with the chapter 16 handout. And I also am considering getting a Wednesday workshop for this section because it doesn't really benefit you guys on Thursday. Are you guys having a quiz or test this Thursday? Okay.
Yeah, we do.
No. No, this
No,
is
no test.
No, Kelly.
okay. I'm sorry. Okay, great. No
Prepare.
tests. But
Hey, what?
There's no test, so you're safe for this
For a week.
Yeah.
okay, then that's good. So then
Next week we'll have our chapter 15 test.
Next week.
Yeah.
Okay, perfect.
Wednesday. Next week.
Okay, great. So I'm just gonna change that. So instead of Wednesday, we're not gonna have it this Wednesday, but we'll have it next Wednesday because you guys can't work on it. And also, one more thing.
What's up?
So Thursday, I said that we'd cover chapter 15. Well, it doesn't even matter. You guys don't even come on Thursday. But there's no test, so come on Thursday, and we're gonna cover a lot more of chapter 16 instead. All right. So ice tables on Tuesday. Thursday is gonna be most of chapter 16. Okay. All right. See you guys
Okay,
later.
thanks.